penetration model with effective potential, which calls some power. And when we collect that, we should make some representation of the data. To do so, we develop the analytical model, which is based on some effective potential. This model should provide accuracy which is enough, which is so not the same accuracy than the theory, and it will be good if it will depend on the parameters which have a clear physical meaning. And I will show this model. First of all, we will discuss not a cross-section part of astrophysical factors, which are simply renormalization of the cross-section by including of penetrability to the Coulomb barrier. You can see what the cross-section is a very rapid function of the energy, but the astrophysical factors are more or less not so rapid function, and it's much easier to fit such a function. Of course, this is plot based on the assumption that we don't have any resonance. Resonances are not included to this database and should be added specially, because it's much more difficult task to describe resonances. And as an example, I demonstrate some reactions where the points are experimental results and the line is the results of the model. For the astrophysical application, we need the astrophysical factor and the energies close to the gamma peak range. And you see if we have typical temperatures for the neutron star crust from 10 to the 9 to 10 to the 8 to 10 to the 9 kelvins, the typical energies are a few MeV. You see what we don't have any data points in this region. So we really should apply the theory. And we, based on the method based on surrounding power potential, which is quite simple. We use some nuclear potential and add to this the tensors associated with multipolarity of the wave. And after that we calculate cross-section as a sum of a wave of different multipolarity with depend on the penetrability of the barrier and probability of the reaction if the particles comes to enough close distance. We suppose when the reactions take place, if the nucleus comes to a close distance, the reaction takes place. And the model is written here for the potential is based on the Coulomb model plus the relation associated with the nuclear forces. Which model is quite simple. It depends on the distributions of the nucleonic on the nucleus, which is supposed to be spherically symmetric, and we should just calculate this integral. The main problem is to calculate these distributions of the nucleons. And we present a large set of nuclear reactions, approximately 5,000 of the reactions. And at this reaction, almost 100 of the nucleus can participate, just from the beryllium to the silicium. And you see it's quite large database. And here we discuss the nucleus with very large number of neutrons, because in the neutron stars, such a nucleus can be much more stable, because even stable, because we have a very large Fermi energy of electrons, which can be much more than the electrons can be very relativistic. And here we present the number of reactions. Finally, we have almost 5,000 of the reactions, and for each reaction we have dependence of astrophysical factor of energy, and you see we have very large amount of data to fit. An example of this data are shown here. Here is astrophysical factor for carbon plus carbon reactions for different isotopes of the carbon. You see what we have at typical points, which is barrier energy, Coulomb barrier energy, and the shapes are quite common, but astrophysical factor is not as strong as the cross-section, but quite strong function of the energy. For different isotopes, for different elements, we have a large variety of values of astrophysical factor. So we should describe this in one model. Can be quite difficult. To do so, we introduce a model potential. which not depend on the nuclear shapes or something else. It is very analytic. It's just Coulomb potential for some, if a distance is larger than some distance, which is parameter of this model. And after that it became parabola. It's very simple analytical potential. It's only thing we should do is to fit parameters of this potential. In fact, it depends on the two parameters for one reaction. After that, we can calculate astrophysical factor analytically with this potential. And the astrophysical factor for the S-waves can be written in this form, and parameters can be calculated analytically. I don't suppose what you have done to describe these equations, but you can find it on the conference paper. If we also should include contribution for the high multipolarities, which is can be done model way by amplification of the astrophysical factor for some value which depend on the typical centrifugal energy, and finally we write the astrophysical factor in this form. As a result, we have just 4 parameters to describe the astrophysical factor for each reaction at energies which are lower than the Coulomb barrier energy. If we want to describe the high energy, we can write the same ideas what we use in the barrier penetration model and write the cross section in the same form and see what if we have energy just the same as the Coulomb barrier energy, just S channel is open, and we can analytically, when we know, we use cross section, and we can define this parameter. To describe the high energy, we apply this result, which is suggest to apply this equation, which is based on the inclusion of high multipolarity, which barrier becomes the classical barrier becomes the energy becomes higher than the classical barrier. As a result, we have just 3 parameters for each reaction. And these parameters were fitted, all data to fit this 5000 reaction are shown here. And the result is simple. We have quite compact, you see, just 5000 reactions, and for each reaction we have a function, 5000 or approximately 5000 functions, just few numbers to fit these reactions. And accuracy of this fit is very good. It's in the worst case it's factor of 3, but the accuracy of the calculations seems to be lower. And all fitting parameters are the same order, which means what we have based on the real physics, and one of these parameters is the typical distance where the nucleus can interact by the nuclear forces, and it is also have real physical meaning. And the result. We calculate cross-section of astrophysical factor for almost 5000 nuclear reactions and summarize these results in the form of a simple analytical model. This model provides possibility to approximate astrophysical factor for a large number of reactions by a few number of parameters, and each parameter has a simple physical meaning. It's also right possibility to extrapolate results for other reactions because all parameters have almost the same value for different reactions. We can, in fact, extract the effective potential of a nuclear reactions rates from the given astrophysical depends on astrophysical factors from the energy, and we have the ability to describe some uncertainties in which define astrophysical factors, because in the Newton star, especially in the deep areas, we have a background of 3 newtons, which is not included for these 4 factors, and maybe we have some idea to include these features, and we can include it to this model, maybe by increasing the radius when the nucleus became interact by the nuclear force, or something like this. And the additional reason why I present this talk here is to attract your attention what strongly subbarrier reactions of maybe typical elements as carbon plus carbon or very neutron enriching elements can be important for physics and have real astrophysical applications.